Did you know that reinforced concrete has a hidden weakness, which turns buildings into a ticking time bomb? The buildings won't explode, but after 50 to 100 years, sometimes even earlier, many of those buildings will need to be renovated or even demolished. But there is more. The material is linked to the disappearance of entire beaches and responsible for insane amounts of emissions. But there might be solutions, which has been passed down to us through the ages. In this video, we'll discover the dark secrets of concrete and reinforced concrete. We'll learn about some cool, little known solutions that might make the material more sustainable and far more durable. And why modernist architects fell in love with this material in the first place. And how this material's redemption could be found in techniques the ancient Romans and cathedral builders already used. In other words, I guarantee that by the end of this video, you'll be able to explain some of the biggest drawbacks of concrete and some of the solutions to get around these. So let's get started. Concrete. The construction industry loves it. The material is just so convenient and versatile, as it can be poured in all kinds of forms, giving designers a lot of freedom and enabling engineers to create ever more crazy buildings. Every second, all around Earth, 950 tons of concrete are poured. That's almost 48 fully loaded trucks. Modern concrete consists of 4 elements: Portland cement, aggregate or little rocks, sand and water. The cement is the most important part, as it is the glue that binds the aggregate and sand together. After the mixture is poured, a chemical process hardens it and it becomes a solid material. Concrete, when it is used bare, is called béton brut by the French, which is what gave us the word brutalism, the name for a certain kind of architecture I'm sure you all enjoy seeing. The first forms of primitive mortar were already discovered in the oldest construction known to this day, Göbekli Tepe, which is 12,000 years old. But it was the Romans who started using proper concrete, or opus cementitium, a material they loved to use. In the Pantheon, for example, a building that stands to this day. But the Romans used this material in compression only. So why exactly is that important for concrete? You see, concrete is strong when it is compressed, when it is pushed together. But when you place concrete under tension, or when it is pulled apart or bent, it is weak. The Romans used concrete in such a way that its compressive strength was used, by using the geometry of the buildings to make them stable. For example, they would use arches and vaults to carry forces to the walls and pillars, which can take on big compressive loads. But nowadays, due to a revolutionary invention, we also use it in a very different way. I'll return to that in a minute. After Roman times, a long period followed in which concrete was barely used. It was almost forgotten. In the 1700s, innovation picked up again. And then, in 1824, a massive invention followed that would create a form of concrete we know to this day: Portland cement. This new, much harder type of cement was formed by combining limestone and clay that was burned to change its chemical properties. But this invention only brought us a little step beyond the ancient Romans. There was one more invention that would make concrete even more useful and versatile, thus completely reshaping the face of the earth. And that discovery was reinforced concrete, in 1849, by a Parisian gardener called Joseph Monnier. Remember how I mentioned the Romans used concrete in compression? And that later we would start using it in a different way? Well, when you embed steel rods in concrete, which are able to stretch and bend much better, the resulting product is suddenly able to take on the tension forces too. In short, a new super material was born that could be used to create beams and plates that could hold weight under tension, like, let's say, for bridges or floor plates in buildings. This property was, until that time, reserved for other materials like wood and steel. Before, if one used rock-like materials like brick or stone, you would need to rely on either heavy stone lintels or arches and vaults to span distances. Those solutions worked perfectly well, and they still do. But with this new invention, it was suddenly far easier to just slam a reinforced concrete slab on top of some pillars and voila, you now had a cheap, rapid way to build with large floor spans. Reinforced concrete took the world by storm. It really did change how the face of the earth looked, by changing the way how we span distances and giving us a new way to build in general. But this new invention introduced a new hidden problem. A problem that not many people speak about. One that would prove to be the Achilles heel of reinforced concrete. Before we cover that problem, I'd like to tell you about something else. I'm working on a new handy overview of some of the places I make videos about. For this purpose, I use Squarespace, the sponsor of today's video. Squarespace makes it incredibly easy to make websites. It allows you to build one either from scratch or to use one of the many beautifully designed flexible website templates. Designing your website is super simple with the Fluid engine. And the all-in-one platform offers everything from email campaigns to analytics. Check out squarespace.com for a free trial. And when you're ready to launch, go to squarespace.com/theaestheticcity to save 10% on your first purchase of a website or domain. And now, let's get back to it. Like I said, modern concrete consists of 4 elements: Portland cement, water, aggregate and sand. But in reinforced concrete, one extra element is added. Steel rods are placed in the concrete, called rebar, which gives reinforced concrete its tensile strength. This creates a first potential problem, greatly reducing the lifespan of reinforced concrete buildings. And that problem is oxidation, or rust. As you might perhaps know, when steel comes in contact with water and oxygen, it starts to oxidate, or rust. And when steel rusts, it expands. The expansive force that presses against the concrete is so strong that it leads to little cracks. These cracks damage the structure, but also allow for extra water to enter. This in turn speeds up the rusting process, leading to bigger and bigger cracks until the structure can actually become unsafe. This vicious circle of concrete degradation is well known, and it leads to the limited lifetime of reinforced concrete, especially in areas near the sea, as the salt in the air makes steel rust even faster. But water can't always get to the rebar, right? What if there's cladding around the concrete building? Or if the rebar is very deep inside the concrete? Then water couldn't possibly get to it. Or can it? There are various ways in which oxidation can and will occur. Multiple chemicals and natural processes have the power to damage reinforced concrete. I won't go into too much detail, but I'll name them here. We have carbonation, the feared chloride attack, the nightmarish sulfate attack, the formidable alkali aggregate reaction, and then there are freeze-thaw cycles, each leading to cracking and eventually to the feared effects of rust. The more bare the concrete and the closer to the sea, the bigger the risks are. It is possible to slow down these processes, so the concrete lasts longer. One way is to increase the amount of cover. Cover is another word for the distance between the steel and the surface of the concrete. The further the chemical reaction or water have to travel, the longer it will take for the concrete to deteriorate. Problem solved, right? Well, not exactly. To make sure this cover is always great enough, first one needs to know how much cover is needed. In the European Union there are norms for this, but not all countries have these norms. And contractors need to cautiously follow all these rules. And this sometimes fails. Even the best contractors deal with mistakes on the construction site. And some contractors don't take rules too serious. Corruption, ruthless profit-seeking and plain old incompetence are widespread. So in many countries and in many buildings, weak spots in concrete buildings will be much more common. And then we're not even talking about the use of low-quality concrete or steel. Even buildings constructed following the most generous norms and with capable contractors often aren't built to last for more than, let's say, 100 years, even though they could last longer. The economical lifespan of most buildings is only 50 years, just enough to repay the initial investment. And this is what many building norms are designed to provide for. After the design lifespan of 50 years, it depends on the circumstances of the building to see what happens. Sometimes the rebar has already begun to degrade. In that case, a thorough renovation is needed, or the building is simply torn down. In the best case, the building can last another 50 years, or even longer with good maintenance. But after the initial 50 years, due to the processes we described earlier, the rebar of many buildings will have begun their inevitable degradation process. Many of these buildings weren't built to be beautiful and long-lasting in the first place. They were built as an investment, and it shows. The will to save these buildings often isn't there, so they are often just demolished. Even if they are refurbished, what does it cost society if this has to happen to every building every 50 years or so? Personally, I believe we should think radically more long-term to be truly sustainable. Think lifespans of 1,000 years, not just 50. That sounds radical, I know, but if we start thinking like that, our building behavior will be radically different too. Rebuilding buildings every 50 years or even 30 years leads to a mentality of, oh, we'll soon tear it down anyways, so we don't have any responsibility to make it really good. We start ignoring factors like reusability, adaptability and beauty. It's our short-term mentality that plagues our society as a whole as well. But there are more problems, which we'll dive into now. Anyone who wants to reduce greenhouse emissions should be aware that the key ingredient of concrete, Portland cement, is one of the greatest causes of CO2 emissions. Up to 8% of total worldwide CO2 emissions are caused by the production of Portland cement. And that is just mind-bogglingly much. Much more than aviation, for example. This emission is caused by the calcination process, where limestone is heated to high temperatures in a kiln, decomposing it into clinker and CO2 gas. So if you want to reduce emissions, how would you do it? I won't go into too much detail here, but one could use other types of raw materials, alternative fuels for the kiln, improve manufacturing efficiency, and capture the carbon. For some purposes, we could even move back to hydraulic lime that was used before the advent of Portland cement, which was created in a slower but less energy-intensive process. However, the easiest and perhaps the best way forward is probably to use less concrete. Problem 3. Impact on the planet. Carbon emissions aren't the only impact concrete has on the planet. One thing many people overlook is the many ingredients of concrete that each need their own hole in the ground, so to speak. All the ingredients of concrete, like sand, gravel and limestone, need to be extracted somewhere. And sand, for example, is already getting scarce. Desert sand, which is plentiful, can't be used for concrete because it is too rounded and polished by the winds blowing it around. This rounded sand makes concrete weak and extremely dangerous to use. No, sand is needed from riverbeds, as this river sand has the rough edges that help it to bind the mortar. The scarcity of sand leads to bizarre problems. The immense Chinese and Indian construction industries, for example, need so much sand that prices have skyrocketed, and a black market for sand now exists. Sand mafias use unethical practices to win this material, from the Caribbean to Africa to Asia. Riverbeds in sensitive ecosystems are sucked up, and even beaches are being stolen, often in the most vulnerable places. Our modern lives are literally built on sand, and the use of concrete is making this worse. Why are we so in love with reinforced concrete? For that, we need to travel back to the beginning of the 20th century, when industry continued to reform society, and a new architectural ideology was formed that fully embraced new industrial construction materials and methods. Modernism. The modernists embraced reinforced concrete like no others, because of its ability to achieve daring new forms with it. Forms that broke with the traditional. Forms for a brave new world. Because that's what concrete allows builders to do. With reinforced concrete, architects could now make shapes that seem to defy the laws of physics, or create massive buildings with huge floor plates cheaply and efficiently. Buildings now turned into reinforced concrete frames with curtain walls as cladding, as these were the perfect match for open floor plans, which modernists loved so much. Instead of heavy but durable load-bearing walls, a reinforced concrete skeleton now supported everything. This reduced the lifespan of buildings, because the strength of these modern buildings was now tied to how long the material could hold under stress. While before, as we already saw, buildings relied on the stability of their form, which led to buildings that could last much longer. Apart from that, modernist architects also loved to use bare, exposed concrete in their designs. Just take a walk outside, go to any place with modernist buildings and you will see it everywhere. When concrete is exposed to the elements, it's more vulnerable, and its degradation can happen much faster. Aesthetically, the stained, eroded concrete can make any place look miserable. A final effect of the embrace of reinforced concrete by the modernists was that it helped cement today's construction and concrete industry in place. Pun intended. And as a sad side effect, craftsmanship was basically exterminated, as well as the use of traditional construction materials. Today, we have to deal with the results. Cities that look grey, with countless of weathered, bleak concrete buildings, and a construction industry so dependent on concrete that they don't know how to change, even if they wanted to. Contractors have mostly lost the know-how to build with the longer-lasting, more sustainable methods and the time-tested materials we know from before. While these might be exactly the solutions we need to solve today's problems. So, isn't there any hope? Well, happily there is. Because the laws of physics don't really change over time, we can still use concrete in another way, making use of its compressive strength. We can do this in two ways. One is to build like we did before, using geometrically stable forms like arches and domes. The advantage is that it's very beautiful, but the disadvantage is that it's not always cheap or practical to create giant barrel vaults for every project. Sometimes it's very handy to have a concrete floor plate that spans larger distances, but even then one can use compressive strength to their advantage. That's where a Swiss company comes in, called Vaulted, who learned from the cathedral builders by using ribbed vaulting to create a floor plate that doesn't need any steel reinforcement and far less concrete. The floor plate is basically a very flat dome, which transfers the forces through ribs down to the corners, making smart use of the compressive strength of concrete. The floor plates still need to be inserted in some form of frame, but it is an elegant solution. I'm very curious to see if their floor plate product will take off. Instead of concrete, we could always use other materials. One modern material that has become very trendy is cross-laminated timber, which is now being used even for high-rise buildings. Although it is supposedly sustainable, it is not known yet how long CLT can last. Then there is natural stone. One of the funny things about concrete is that the very same limestone that is dug up to be crushed, burned and used for the clinker is in many cases an excellent, long-lasting and low-emissions building material when used as stone blocks. When it is sawed in square chunks, it can be used to build perfectly strong and durable buildings. And we're not talking about marble here. A lot of stone might not always be pretty enough to use for the cladding, but it's often good enough for the structural walls. Using limestone like this means it doesn't have to go through the CO2 intensive burning process, except for the mortar needed to bind the stones. And it also doesn't need as much of the precious river sand. And finally, limestone can be truly beautiful, like the limestone in Bath, or the Belgian blue or hard stone. So what should we do? If we want to build sustainably, it is essential that we respect the forces of nature and that we build with long-lasting materials instead of using materials with hidden problems like reinforced concrete. We can still work with the forces of nature to create buildings that sustain through their geometry. In that case, we can even continue to use concrete. There is a reason that the Pantheon still stands after 1900 years. Also, using these efficient forms like the arch and the dome leads to incredibly beautiful buildings. By using less concrete or using it in smarter ways, we can not only emit less CO2, we can also save fragile beaches and riverbanks from the sand mafias, reduce the power of an already far too powerful concrete industry, and most importantly, we can start building more beautiful and long-lasting buildings and infrastructure again. And that, in the end, leads to a more pleasant world to live in. What do you think? Should we indeed look for alternatives for concrete? Let me know in the comments. If you like this video, you will love the next one about a town built by King Charles that defied all the odds. Thank you and see you next time.